Have you ever stopped to think about how your computer can possibly simulate something as smooth and flowing as water? I mean, at its core, a computer just understands on and off, right? Ones and zeros. Well, it turns out there's this amazing mathematical bridge that connects our smooth, continuous world to the step-by-step digital one. Let's dive in and see how it all works.
So, at the very heart of this are two totally different ways of looking at change. On one side, you've got continuous change. Think of it like a movie, where every single moment just blends seamlessly into the next. But on the other side, you have discrete steps. This is more like a flipbook, one distinct snapshot at a time. And this fundamental difference is exactly what we're going to unpack.
All right, so how do we actually describe these two worlds with math? Let's take a look at the actual tools that engineers and scientists use for everything from predicting the weather to figuring out your bank account.
For that smooth flowing world, we use something called a differential equation. Now, its whole purpose isn't just to tell you where something is, but to describe the rate it's changing at any single instant. It's the mathematics of things that are in constant motion.
Just look at the water level in a tank like this one. It's constantly, infinitesimally dropping. It doesn't just jump from full to half full. A differential equation is what captures that entire unbroken story of the water draining, not just a few snapshots along the way.
Now, for the digital, step-by-step world, we have difference equations. This is the native language of computers. Instead of a continuous flow, it calculates the state of a system at specific points in time, kind of like your savings account. It doesn't grow constantly, right? The interest gets added at the end of the day, or the month, or the year. Each one of those calculations is a single, discrete step.
Okay, so we've got these two different worlds. How do we build a bridge between them? How do we get a computer, which only thinks in steps, to understand a reality that's totally continuous? Well, this is where the mathematical magic really happens.
So, here's the secret sauce. We can't make a computer think in infinitely small moments. It's just not possible. But what we can do is make the steps really, really, really small. We can get a pretty good approximation of a smooth curve by just calculating a whole bunch of tiny, straight lines from one point to the next. And that, right there, is the bridge from the analog world to the digital one.
And engineers have a few different ways to build this bridge, depending on what they're trying to do. You can figure out the next step by looking at where you are now and a point in the future. That's called a forward difference. Or you could use the present and a point from the past. That's a backward difference. Each method gets the job done, translating that smooth change into digital steps a computer can handle.
Okay, so now that we're living in the digital world, we've got access to some incredibly powerful tools. Let's look at one that helps us understand how a system's past sort of echoes into its present and future.
The term is convolution. And I know, it sounds a little intimidating, but the idea behind it is actually super intuitive. Seriously, think of it like an echo. When you clap your hands in a big canyon, the sound that comes back isn't just your clap, right? It's a mix of your clap and the unique shape of the canyon itself. Well, convolution is just the math that describes that exact mixing process.
So, to figure out the final echo, we need two things. These graphs show signals over discrete steps in time. That's what the little n in brackets means. On the left, that's your input signal, your clap. We call it X and N. And on the right, that's the system's own unique personality, its impulse response. We call that H and N. Think of that one as the shape of the canyon. It's how the system reacts to just a single sharp input.
The process itself is kind of like a rhythmic little dance. First, you take that system response, the shape of the canyon, and you flip it backwards, like a mirror image. Then you just slide it across your input signal, one step at a time. At every single step, you multiply the parts that are overlapping, and then you add all those products up. That sum gives you exactly 1 point of your final output. You just keep sliding, multiplying, and summing to trace out the whole thing.
And voila, this is what you get. The output signal, Y sub n, isn't just the input, and it isn't just the system's response. It's a true blend, a convolution of both. You can literally see how the sharp, original inputs have been kind of smeared out and reshaped by the system's memory. Pretty cool, huh?
So why does all this math about steps and memory really matter in the real world? Let's take that simple idea of a difference equation, just one step at a time, and see how it can unleash what's been called one of the most powerful forces in the universe.
Let's set up a really clear, real-world example. Imagine you start an investment with $10,000. Simple enough. Every single year, you add another $1,000 and the whole thing earns 6% interest. It's a classic step-by-step financial system.
Now, this whole process is run by a super simple difference equation. The rule is just this. The amount of money you have this year, A of n, is just the amount you had last year, A of n minus 1, times 1.06 for the interest, plus that new $1,000 you added. I mean, look at it. It seems so simple on the surface, just a little multiplication and addition repeated over and over.
But what's the actual effect of that tiny repeated step? What happens when you just let that little equation run year after year for a full 40-year career?
The result is, well, it's absolutely staggering. If you had just left that initial 10 grand alone, it would have grown to over $100,000, which is awesome, don't get me wrong. But by adding that simple, repeated $1,000 step each year, the final value just skyrockets to over $250,000. That is the incredible power of a simple rule applied over and over again.
It's a force so powerful that, legend has it, when Albert Einstein was asked to name the greatest force in the universe, his answer wasn't gravity or nuclear energy. It was compound interest. And what is that? It's just the result of a simple difference equation, relentlessly stepping forward through time.
And that leaves us with a final thought, right? From the way your phone processes audio to how we model population growth to the entire financial market, these mathematical tools are absolutely everywhere. So if a simple series of steps can describe how a fortune is made, what other complex, powerful, and beautiful things in our world are just waiting to be understood one discrete step at a time?